All right, so this is a Math 1105 video about rational functions. So the first thing we'll look at is what we mean when we say rational function. So just like with a rational number that is a real number divided by a real number, a rational function is a polynomial divided by a polynomial. Okay, now we know that in real numbers there's a restriction down here in the denominator. Same thing here with rational functions. Whatever's in the denominator, whether it is the polynomial itself or the value it takes on, can never ever be zero. So that'll be the first thing that we look at. We'll remind ourselves about the domain of a rational function and then also what happens if that's zero. There are a couple of possibilities. If the denominator is zero, what could happen to the graph at that point? All right, so first of all, the domain may not include any value for which the denominator is zero. We already know that. We knew that from the very first time we talked about functions, that this particular type of function has a restriction on its domain. Okay, so now let's talk about what happens if the denominator is zero. What could happen is that we could have something called a vertical asymptote, which is when the denominator is zero and there's no way we can kind of cancel it out, if you want to use that word. There's no way we could reduce that piece out. So the way we find what happens there is called a vertical asymptote. And a vertical asymptote is an imaginary vertical line. Imagine that's vertical. So it's a vertical line that isn't really part of the graph. It's not really there, but it's a place where the graph cannot touch and also approaches negative infinity or positive infinity as it gets close to that line. So not only is the graph not defined at a vertical asymptote, it's like super undefined at a vertical asymptote. So much so that the graph kind of goes crazy when it gets near the vertical asymptote. Okay, so this is called a vertical asymptote. Okay, weird word. These look like all vertical lines, or the equation looks like all vertical lines. X equals some number. So this might be like x equals 4, okay? But these happen, again, where the denominator is 0. And not only is the denominator 0, but it's 0 even when we have reduced the function as much as we possibly can. So let's look at some examples of what vertical asymptotes are. So we're going to determine vertical asymptotes. Okay, so here's our first function. Is it plus 15? No, it's minus 15. Okay, so in order to find out what our vertical asymptotes are, we first need to know what this thing looks like when it's completely reduced. So whenever we reduce a number, we cancel out common factors. Whenever we reduce a rational function, we again cancel out common factors. So we're going to factor the numerator and denominator. Okay, x squared plus 1 is a sum of squares. In general, that doesn't factor. So there's nothing we can do with that one. The denominator, though, is a trinomial with a leading coefficient of 1. So we know it could factor. And if it does, its factors are going to start out looking like this. Okay, the other numbers in parentheses have to have a sum of positive 2 and a product of negative 15. So if we think of some factors of negative 15, that could have a sum of positive 2, positive 5, and negative 3 will do it. Okay, so now we look here and we try to reduce. I don't see any common factors. Let's remember that unless you can factor something out, you cannot reduce it out. So this is an x squared and this is an x, but x squared is not a factor up here. and x is not a factor down here. So for instance, these don't count as common factors that we can reduce out. So this thing is already reduced. So these two pieces right here are where we get our vertical asymptotes. We need to look at the zeros of the denominator that are left down there after you've reduced. So we can't reduce this. So our vertical asymptotes, which I'm going to abbreviate VA, are going to be given by the zeros of what's left in the denominator. So -5 would be a 0 and +3 would be a 0. So these are our two vertical asymptotes. The graph is not defined there because it makes the denominator 0. And not only is the graph not defined there, but this function is going to go crazy. It's going to go up to positive infinity or down to negative infinity as we get close to these. So if you want to visualize the graph, we have x equals -5 here, x equals 3, and the graph is going to kind of happen around them. We're not so worried about the graph. We just want to be able to find these asymptotes. Okay, let's look at another one. Again, we're determining vertical asymptotes. All right, and I'm going to make one up because the next one I have isn't super great. I mean, we're going to do it. It's just not great for the next example. So let's look at x squared minus 4 over x squared plus 5x plus 6. And cross our fingers this works like it does in my head. Okay, so we need to start by reducing this. We reduce by taking out common factors. So we can factor x squared minus 4. Sum of squares doesn't factor, but difference of squares does. And in this case, it will factor as the things being squared. We look at their sum. We look at their difference. So that's how the numerator factors. The denominator is, again, a trinomial with a leading coefficient of 1. So if it factors, we know it's going to start out looking like this. These two numbers have to have a sum that is the same as 5 and a product that's the same as 6. So the only way that can happen is if they are +3 and +2. All right, so we factored the numerator and denominator. Great. Now let's stop here and just make an observation. This function is not defined at -3 because it's a 0 of this factor, and it is not defined at -2 because it's a 0 of this factor. So the function is not defined at -3 and -2. No matter what happens from here on out, -3 and -2 are still no-nos in the domain of this function. But if you'll notice, x plus 2 is a factor of both the numerator and the denominator. So we can kind of reduce those out, and we end up with a completely reduced function that is x plus 2 over x minus 2 over x plus 3. This piece down here is the only piece that creates or contributes to a vertical asymptote. So we are not defined at -2, and we'll talk about what happens there in a second. Still not defined at -2, but -3 is where we have a vertical asymptote. Okay? Now, let's talk about what happens at -2. At -2, we're still not defined, like we said before, but instead of having this imaginary line where the graph kind of goes crazy up and down, at -2, there would just be a hole. So the graph would, I don't even know what it looks like, but the graph would continue on as normal, whatever. There would just be a hole at -2. So that's what happens if a factor cancels out. It does not become a vertical asymptote, but still we have something weird that happens there. And that weird thing that happens is that there's a hole. But we are really interested in the asymptotes at this point. Let's do one more of these. Okay, so the last one we'll look at is this one. All right, now just by looking, we can tell that putting a 1 in here is going to be bad. 1 is not in the domain of this function because right away we can see if x is 1, the denominator is 0. So we're not allowed to do that. Now, is it a vertical asymptote? That's what we have to find out. So we find that out by first factoring and canceling what we can. So these two terms both contain an x. Right, what's left over, that would be an x minus 1. And now we see the x minus 1 is a factor of both of these pieces. So x minus 1 is gone, and we're just left with x as our completely reduced function. Okay, I mean, this function reduces down to x. We are still not okay at 1, all right? But since we don't have anything left in the denominator that could be 0, like everything in the denominator was reduced out. What ends up happening here is that we still have a problem at 1, we'll still have a hole there, but it's not a vertical asymptote, and there isn't a vertical asymptote. So the answer here is no vertical asymptote.